the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
All right, well, I guess we'll get started. Hi, welcome to Beyond Compilation Databases to support C++ modules, build databases. My name is Ben Boeckel. I work for Kitware. I've been doing build systems and software process stuff for about 15 years now. I'm a CMake developer. I've been designing, implementing features, doing performance improvements, and then on the using side, I've been maintaining and improving build systems that use CMake for 10 plus years. And most recently, I've been working on C++ module support within CMake and across the ecosystem. At Kitware, we're working with the community to try and improve building software for everyone. This includes going to the ISO meetings, doing standardizing formats for dependency discovery for modules, pushing forward modules in other build systems. For example, CMake and Boeckel now support modules. Due to, I've been reviewing code and prodding them to, hey, here's how CMake's gonna do modules. Maybe you should start considering supporting them too. So for this talk, I'm gonna be going over compilation databases, which I'm sure many of you have used. So what are they? And then how do modules change their usefulness, more or less? And then a solution that I've been working on, which I call build databases, and how it solves those problems. So first, compilation databases, they're JSON documents. They are just top-level arrays with objects in them, and each object describes a single command that happens within your build. You have the working directory where the command gets run, the command itself, what source you're compiling, and what file it will create on the output. However, that is optional, which can cause issues. We'll get there. They're specified by the Clang project. They're not ISO, they're not even like LLVM. Clang is the one that specifies it. They are, however, widely used and available. Build systems will generate them across the board pretty much. I think Boeckel is the major one that doesn't do it. And then static analysis tools and IDEs will use them to understand, I'm looking at your project, what does this mean? Because just source on it, C++ source on its own is not very meaningful without knowing what flags you're passing to it. So here's an example. You have your directory where you're running it, your command, which is a string, basically flag soup, and then the file you're compiling, and output. I have a pointer. These are generated usually by your build system, for example, CMake or Maison. You can also have your build tool do it. Ninja has support for doing it. And there are also tools which will wrap your build and discover what your build commands are. They're usually, if they're done by the build system, they're available with your build rules. So when your make file or your build.ninja is generated, you'll have your compile command so that your IDE can just start understanding your source code. This is usually good until you have things, there are exceptions to this, which we'll cover in limitations. If you miss the output field, your source files can be ambiguous. You can compile a source file more than once, whether it be for I'm compiling it in release mode and debug mode, or you can have it because you added the source to multiple targets and it has different flags. In this case, your IDE needs to understand which one matters. Visual Studio, for example, has a dropdown for which configuration am I using. And it also understands which target am I working on by which project you have open. However, VS Code or Vim are not necessarily going to understand what is actually happening. You also have the string representation for your command. It is specified to be shell escaped, which is woefully underspecified. On Unix, you can generally just assume bourne shell. And then on Windows, you have to, it's usually CMD, but some people use PowerShell. and your escaping sequences are very different in those cases. But there is no place to tell it what you're doing other than looking at it and guessing based on heuristics. There's also no extensibility. There's no place for reserved field names. And so adding any new fields to this format is fraught with conflicts of what else anybody else has been doing in the ecosystem. There's also a portability issue. All your flags are dependent on what the compiler is in use. So you can look at it and be like, oh yeah, I totally know what that flag means, except it's not supported by that GCC and it's actually an error. The other thing, you don't know what your build graph is. You don't know if they're generated headers you're going to be expecting. You don't know if there's generated sources you're not going to be finding. Those you can usually be like, okay, they're not on disk, so we can expect them later. But there are also arguments that take files which may not exist. For example, you could have -include, some generated file. And then for modules, there are files that CMake, at least in its strategy, will write out during the build that your commands then read during the build. And so your configure time information is incomplete. That brings us to C++ modules. So surprise for anyone who didn't know, modules complicate compiling C++. The old days of embarrassingly parallel, I have n cores, here's n jobs, is over. This is because C++ has said, great, we will take the Fortran compilation model and use that. So this means that when you compile a source file, you will get your object file. You will also get what is called a BMI. This is built module interface or binary module interface. Some implementations called a CMI for compiled module interface. This is basically an extra file that when something imports a module, that's what it's looking for. But you know, it comes out with the compilation. So it's not ready right away. So with C++ and Fortran, the similarities between them, they both have compiler-specific BMIs. You can't use a GCC module on Clang, vice versa. And with C++, it's even more strict where the flags matter. If you have, your module is compiled with C++ 23, if you have something that says, I want to use 26, and it tries to import your 23 module, it won't work because the BMIs are basically abstract syntax tree dumps. And when the standard changes, the AST changes, which means that you can't read it anymore. The other thing we have with Fortran, in common with Fortran, is that what module you're looking for is in the source. You don't know just based on some inherent property what module is going to be created or which modules you're going to use. So you have to look at the contents. This means that you have to either, every time a source file changes, go and rebuild your build graph, or during the build, discover what your build graph is going to look like. I'll get to how CMake does that in a bit. The differences are in details. Fortran supports what they call submodules. They're basically just forced nested modules, and then they also support multiple modules exported from a single TU. C++ does not do that. Instead, it has partitions, but partitions are pretty much modules. You just can't import them directly. And then, again, Fortran doesn't have the flag problem that C++ does. So a bit of a history on how Fortran modules got built. So they were introduced in Fortran 90. The official documentation from one of the vendors was run a parallel build until it works. This is fine until you write cycles or you import something you don't make, which means that you end up with a build that never ends, following their instructions. Eventually, someone wrote make f90dep, which will look at your Fortran source and write out a makefile snippet that says, when you compile this object, you need to first compile this one. And then you can include it in your makefile, and you'll get a reliable build. Brad King, the current maintainer of CMake, imported this into CMake and implemented it for the makefiles generator in the late 2000s. And then in the mid-2010s, he went to Ninja, implemented dyne-det support, and we carried that patch set for about 5 or 6 years until it was finally merged. That came out in 1.10. We were very happy when that was released. So now everybody can use upstream Ninja and build Fortran modules. And this is one of the upsides of C++ choosing the Fortran module strategy. This is a solution that already exists. So for the example, we're going to have a C++ module target. This is the CMake code for it. We have a library A. We're going to add some sources to it, A2 and A3. These are regular sources. They can import modules, but they do not provide them. In order to provide modules, you need to tell CMake it is in a file set of type CXX modules. A1 provides a module in this example, and then we also need to say we're using at least C++20. Here is a simplification of the build graph that we end up making. So you have your source files on the left here. We don't know anything about the dependencies between them. So there's a scan and collate in the middle. This is where we do the magic, figure out what the dependencies are, bring them together, and then we write out this a.dd file during the collation step. This tells CMake what happened so that it can use it in further steps. It also writes out a file for Ninja to understand that here we have discovered that A1 generates a module named math, and then A2 happens to import it. So this the collation step will basically tell Ninja, don't compile A2 until you compiled A1. And then A3 doesn't care, so it can go ahead and do that. This comes from a paper I presented in ISO in 2019 about how CMake does Fortran modules. These clouds can basically be implemented a couple different ways. And then we have these numbers on each box is the order that you can compile them in. So these are all zeros because they're ready. And then we scan and collate first. We get the DD file as second. And then A1 and A3 can go next because they don't need to depend on anything else. And then once everything's ready, we can link them and put them into a library. All right, so now we have more than one library and we need to link between them. We have our library A, we're gonna add sources to it. We have library B, we have other sources. B links to A, same with C, it has sources, we link C to B. Here is how CMake links these together. So we have each library will scan independently. They'll figure out their dependencies. The collation step will take its target's dependency information and any targets it depends on. So for example, the collation of A doesn't need to consider anything else because A doesn't link to another module using library. B will look at that and say, oh, I can also use A's modules. So it will go and look at the collation output of A, so it can say, oh, hey, I see you import something from A, it's over there. All right, so with that, we have an example compilation database entry for a single source here. Is there anything missing? Can we brainstorm on what is missing to make this useful for modules? Any ideas?
What are the dot rows it's waiting for?
Yeah, the ordering of the compilations. We have no idea what order we should run this in with any other command.
What modules it produces.
Yes, we have no idea if it makes a module.
I guess if you want to import other modules, they might not be related by name. You might want to have some mapping for that.
Yeah, so we also need to know what module it imports. Anything else? This one's subtle. It's this thing, if it makes a module, can you use it in another target? So for example, if A makes a module, it doesn't mean that B can use it necessarily. It might be a module private to A. So you need to know that this is not useful outside of A. So CMake currently will do these things internally, but we need to communicate this to tooling. So internally, CMake will smuggle this information through module mapper files, which are basically files that we will generate at build time that are in the command lines that we generated previously, so that when the command runs, they're ready and it knows what to do. This is a big reason why if you try to use compile commands today with CMake and you use modules, it's going to be very confused until you actually run your build, because it's going to say, yes?
The database that gets compiled, does it get compiled early so that it's useful for the rest of the build process, or is it a product at the end of the generation?
You're talking about compile commands or build data?
The build with all the compile commands in it.
So compile commands are generally available there, but they're not necessarily useful. They might be referencing information that is not ready yet. For example, if you generate a source during the build, your compile commands are generally ready as soon as you have the build recipe, but until you run it, that source doesn't exist. So that's one of the problems with compile commands in general. But yeah, just because the file's there doesn't mean it's useful yet. And then the other thing that's not there is flag compatibility questions. So you have your set of flags. You need to know that, hey, this one is going to make a BMI with C++23, but if you come across something that's using 26, you need to know that you can't use that one. So next step is build databases. It's still JSON. We chose JSON because it's a simple format. Everything has a reader for it. And it's mainly tooling oriented. It's not meant to be written or read by humans generally. So there's no need to do YAML where you're not typing double quotes all day long. There is an ISO C++ paper for it. It is 2977. It needs a new revision based on the implementation in CMake. I imagine there will be more, but hopefully I can get that done in time for the next ISO meeting. The other thing is that build databases are only provided during the build. You're not going to get one right after you configure. You're going to have to run at least some of your build to do it. This is basically just the scanning part. However, scanning can depend on compiling other things. For example, if you compile a tool and then you run the tool during the build to make other sources, you need to build that before you can know what modules you're going to import in those sources that don't exist yet. So the way the build databases handles this, we have, instead of just a top-level array of objects, we have groups we call sets. These sets contain the ordering information so that you know that B can import things from A but not from C. It contains the information on the visibility of the modules between the sets. And then the sets are also more or less duplicated based on flag compatibility. So the sets belong to what we call families. All the sets of the same family are related in that they usually compile the same sources, just in different ways. So whether that's because it's a release versus a debug build, or a static versus shared, or 23 versus 26. So the skeleton of the build database, at the top level, we have our versioning information, because we have learned that we need to version our file format so that we can incrementally improve them. And then there's the sets themselves. Within the sets, there's the family name and the name. Then the list of visible sets from each set, and the translation units that belong to each set. Then at the translation unit level, we have pretty much the basic compilation database object. We have the object, the source, the work directory. We have three ways of specifying, or three places we specify arguments. There's the full command line, and then there's two sets of argument lists, which are flags that matter for BMI compatibility. And then we have the module dependency information, whether it's what it's providing, what it requires, whether it's private, those things. So it is versioned. There's a major and a minor version number. The major number is bumped whenever we change the semantics of things. So for example, if we had a better way of representing command lines than a list of strings, we would bump the major version, because you need to be able to know how to read those to actually know what the heck is going on. Also, I would like to put code generation into this at some point so that you can know that this source comes from something, and then you can know what might need to happen for that to be true. The minor version gets bumped if we add things which are nice to haves but are not critical. So the big one is if we get compatibility hashes from Daniel LaRosa's paper, where we can ask the compiler, here's a list of flags. Can you tell me what this means? Or at least, is it any different than this other set of flags? That would help us know that, what flags matter on a compiler basis instead of having to divine it from the tea leaves of the implementations. There are some various other things that can be useful here. For example, if we could get the scanning performance metrics, how long did it take to scan the source? That can be useful for analyzing things, but it doesn't matter for the usefulness of the build database, so we would only bump a minor version number for that. Then we have the sets. So names of sets are globally unique within the database, and then they're related to each other by the family names. And then the visible sets name the sets that you can import from. In CMake, the families map more or less to per configuration targets. So your library A would have one entry for its release build and one entry for its debug build. They would share a family name. And then for compatibility flags, CMake will generate what we call synthetic targets, which are basically instances of the targets that have BMI compilation rules so that they can be imported properly. Currently, as of CMake 330, we only do this for imported targets. This means that inside of your project, all of your flags need to be compatible for it to realistically work. This is a limitation we plan on fixing hopefully within the next year. And then also with this, the visible sets, we can know what the target graph is. So you can know that, this is something core in your project because everything uses it, or this is a leaf. And then, so at translation units, this is where we have the compilation database entries more or less showing up. The object output is a uniqueness constraint. There can only be one entry in the database that outputs a given object. This just comes from Make and Ninja liking only one way to make a thing. You have the source file that's there, the work directory that you're going to work in for any relative paths in the command or in any of the other fields. This is how you can construct an absolute path to know where you're going to work on things. And currently, we only support arguments as a list of strings because shell escaping is not something I want to play around with or try to standardize. Neither should anyone else at this point. Then the additional fields on each translation unit, we need to know what it provides. This is a mapping of the module name to the BMI that it will produce, and what it requires, which is just a list of module names. And then you can go and traverse the target graph to figure out where they come from. And then whether it can be used from other targets is just a Boolean private. Then we have our baseline and our local arguments. So baseline arguments are the flags to apply to things you import because they change the AST. For example, a-stud flag says, I'm using 26, for example. This means that anything you import needs to have a BMI compiled with C++26. This means that you're going to end up possibly compiling 15 different BMIs for a single translation unit if you use them 15 different ways. And then there are also local arguments. For example, if you have a module foo and you include zlib.h in your module, things that use your module don't need to know where zlib.h lives. So your local arguments will say -i where zlib lives, but you don't need to tell that to anybody else. The current status of build databases, it's going through the SG15 tooling subgroup. We're targeting the ecosystem IS international standard, which we are working on making as an additional standard that is produced by WG21. It is led by Rene Rivera There are many authors on it at this point, though. The first things we're working on are response files, and there's a tooling, interoperability, knowing what you support protocol that's being worked on. This is, build databases are P2977 build database files. It's by myself and Daniel Ruoso of Bloomberg. And then in CMake, we have 3.31 will have experimental support for creating build databases. It is only for Ninja generators at the moment, and it only exports information out C++ translation units. We can put C in there, but it's basically a compilation database at that point. So it's not on the top of the list of things to implement. So here's an example of how you create a build database with CMake. We have our experimental flag. This tells CMake, I am accepting that I am using experimental stuff. I understand that if it breaks, it is on me. And the UUID that we set here tells you basically which edition of the experimental feature you are accepting. If it is not what CMake implements, it will ignore you. This way, if we change anything, you basically get notified by things not working instead of things half working. When you want to export build database information, you need to set a target property. The CMake underscore target property name variables tend to initialize these properties. So we will set the variable to 1 to say, I want to export build database information. We have a package that provides modules. And then we make our library A, we add some sources to it, and we want to use that target that we imported with modules. So we go and configure, we're going to build a release build, we're going to use Ninja, we're going to build our source into our build tree. CMake is going to tell us that we're using experimental stuff, which is, that's what we want. So then there is a target that we generate called CMake underscore build underscore database. This is how you get your build database out of a CMake build. So we'll tell Ninja, please go do that. It will run 6 targets, which is basically scanning the source file from with modules, our source file, and then the collation for them, and then actually putting them together into a single database. And then let's look at it, except we're going to mangle the JSON so that we can actually read it on a slide. So we're at version 1, revision 0. It's great. That's what the current paper says. We have 2 sets. We have our target A is the family name. It is the release build, so we're going to do A at release. We have our translation unit. The arguments are not all that important here. It's just they're noise for the example. Then we have our source, what we're going to make. It is a private module to this target. It provides A. It's going to write out this BMI, and it's going to require with modules, and it is run in the build directory. And we can see that it also can use modules from this weirdly named with modules synth target. This is basically how we tell instances of them apart. There's some hashing involved to make them unique. So then we have our set for our imported target. This is something new to CMake. Imported targets usually don't appear in your build graph. However, they need to, because we need to build BMIs for them now. So we have our with modules target. It is imported, so it lives in a given directory in CMake's semantics. So you can have multiples of them that are slightly different. And then we are building it for release, so it gets the at release on its name. We have our arguments for it. We do not have an object file for it. We are not expecting to build an object because we're expecting it to be in the library that with modules built. And when we link to it, that's when we will get any symbols we need. So we do not have an object here. Instead, we have the source. It is not private, and it does not require anything else. And then it provides the with modules BMI at this location. And it does not provide it doesn't need anything else. So it doesn't have any visible sets. So that is the current state of build databases. For the future, we need to get this implemented in our static analyzers, our IDEs. Clang D needs to understand what this is. I would also like to import the structured response files so that we can have more than just a list of strings for our commands. This way we can say, like, here's the command. It is consisting of these include directories, these defines. Here's some warning flags. That way you can actually reason about them instead of having to understand what various prefixes mean on each flag. Eventually, header unit support will show up. Whenever the ecosystem gets around to supporting header units in the first place, we will get there. They're by far the most complicated part of modules that have come. And then also adding non-C++ sources to the database. Currently, there hasn't been much need to do it because nothing else uses modules like this. Getting Fortran in there would be interesting, but Fortran tooling is not up to where even C++ is. So that's what I have. So I'm on GitHub and Reddit at Math Stuff, and then you can find me on the CMake discourse and Kitware GitLab. Feel free to file issues, and then you can email me as well. So any questions or concerns? Comments? Oh, yes, the mic's in the center.
Hi, if you're using a package manager like CppCon and it builds a module, what's the interaction with this?
So modules are, so even if your project installs modules, they will generally install the module interface files and not the BMIs, because the consumer might say a flag that they need a different BMI for anyway. So say your project compiles in C++23. You install C++23. You install your BMIs. If I'm using your project and I want to use C++26, I have to build my own BMIs anyways.
My understanding at the moment is, certainly with the VC package, that actually goes away and builds the BMI file somehow. And you then consume it from VC package.
You can only do that if you top-down enforce consistent flags
yes,
everywhere.
that was sort of my question.
Yeah, that's very hard to do in general, because any project might say, I want to move to C++26, and as soon as they do that, they are now in a separate world and need a completely separate VC package dependency tree. Yeah. So I think the consumers rebuild BMIs is more scalable. Also, they might not use the same compiler as you, in which case it's a different BMI anyway. And by different compiler, I mean like you pulled a new version of GCC. That's a new BMI version today. It is tied to the Git hash of your source tree.
Okay, so. Thank you.
I have two questions. First of all, a compile command, you said compile command.json does not require the outputs file. Mm-hmm. I'm assuming the build database does.
No, it doesn't, because BMIs don't have an object file to specify.
That makes sense.
Yeah.
Another question is, a Ninja target is generated to make these build databases. The example mentioned ran 6
yes.
6 jobs.
Yes.
And how does that scale? Does that increase with the complexity? And
so only the scanning needs to get done. So this didn't actually create any object files, but we did need to get the dependency information from the sources to build the information. So it's O of your number of sources, but scanning is a cheap operation. So
and is it parallelizable to some extent?
Yeah, all the scanning should be independent. Okay. So
thank you.
Hello. I apologize if this is a little bit vague, but we've been hearing for a long time how modules are going to make our build so much faster, and I'm like, okay, but we don't have the tooling to build real programs with modules. So now that you've made that tooling exist, do you have any opinions on that?
I think there is going to be a hump before we go down the hill. So you can tell that things are faster, like on the end, when you're importing std, for example, it's a lot faster than including headers. But the way that std is built right now, it takes about 6 seconds in sometimes. So you'll get a stall while you're building that, and then everything gets to go. Eventually, hopefully we get a bit better with that when when the modules are like better than include everything, export everything. And we actually say like, this new container we made is in stud.containers.x, and then you can import just that. But today, for example, with stud, it is a gigantic module, and you can definitely tell that it is being built in your build graph.
Thank you.
Hi, thank you for that talk. It was really interesting. I've maybe a bit of a weird question about these build graphs, because I'm interested in not just using modules for building C++ projects, but also kind of reading them to gain information about essentially about the AST, right? I was wondering how do you do this with CMake, how you would get access to these VMIs, essentially, because currently there's no standard way of getting those file paths out, while there is a way to do it for object files, DLLs, outputs, and PDBs, for example.
Yes, so I presume you're thinking about the file API?
I don't know what the file API is.
Okay, so the file API is basically where you can ask CMake, I would like to ask some things about the build graph, and at generate time it will dump those out. So you can say like, hey, I'm interested in the target property so that I can highlight things that are wrong in your CMake list. It's generally used for IDEs to better understand what CMake is actually doing. Then that still will not have the information because we don't know it until build time.
Yeah.
So the build database is probably what you're going to end up going for to get this.
Okay.
So,
and there should be, is there plans to eventually have this as like a ability to query where this database file goes in from CMake as well?
So if CMake build underscore database will always write to build database.json.
Oh, okay. Okay.
Yeah.
Awesome.
So there are some intermediate files that we basically funnel down into that. For example, each target makes its own build database, and then we combine them up to the top level.
Right.
So you can also do target-specific build databases if you want to do something more targeted.
Okay. Awesome.
This is similar to the previous question, and if I were smart enough, I'd be able to figure it out on my own. So I'll give you an example. Let's say I have a C++ file, foo.cpp. It has some build things. In that build database, all of the commands on how to compile it are in there. Mm-hmm. And if I want to have a tool, some type of code generator that is based on like libclang, I need to be able to know what flags that thing was compiled with in order to use it. I can do that after I've run all my CMake stuff. I can then go do a separate generation build by reading that file and getting it. But I want it all to be together. I want to be able to specify a rule that says, I want you to go generate this thing based on that thing, but when you generate it, I want you to use all the flags that you would use in order to build that thing. How do I do that?
Currently, the build databases, you could craft the path and depend on them, and it would probably work. But I feel like we want to actually model something for that in CMake to get that information to you at build time. I have a lightning talk where I will discuss features I would like in CMake, and CodeGen features are one of those things. And for YouTube, none of those things at the lightning talk are promised. There are no guarantees of anything. It is just a wish list. So
I would run the normal CMake build command and then have some script that then goes and grabs that stuff, and then how would I re-inject this back in so that it all gets run together?
Yeah, so like I said, you need to kind of use the file that you'd want to use the build database for the target you're instrumenting.
But it's not available while
it's available it's in the build graph. So if you depend on the file, you can go and read it, and it'll be up to date when you need it. We currently don't expose that path anywhere. It's kind of internal, but you could guess it. It's not that hard. But file an issue, file a feature request, and we'll see what we can do when we when we get to things we can do now that we have these cool things.
Thank you.
Thank you for the talk. You mentioned that it's just Ninja that's supported currently. Is there a reason for that, and is there a roadmap to include other build tools?
Yes. So the reason it was only supported in Ninja is that currently the only generators that support modules at all in CMake are Ninja and Visual Studio. And in Visual Studio, the dependency files that we read this stuff from are internal MS build. So we don't have access to them to get the information. It's a request we've made. Because currently also we can't enforce private modules in CMake with Visual Studio because we can't intercept that and say like, no, you can't link that. But yeah,
Thanks.
Hello again. For same train of thought, I am for reading those files. I also would like to generate, kind of similar to the question before. I would like to generate code from essentially what's in those ASTs. Are there plans to allow something like that to be kind of like having a custom build step that you can inject like in between the scanning or like the pre-process BMI stage and the proper compilation stage?
there are no plans for it. I feel like before we can commit to anything, we need to figure out what we're doing for makefiles. Because the makefile generator is structured differently, and there's a lot of work needed to make modules work well. So before we expose this cloud here, we need to figure out what it looks like in every generator. There are other things about this cloud. For example, it can be structured there's 3 different ways in the paper here. We only implement one. They each have pros and cons. The one that is implemented is best for incremental builds. One-shot builds, like from CI, would be more interested in a single scan of all the sources at once instead of per source scanning. And then there's also combining this. When you have that, you can also just collate at the same time. But only one of them is implemented today because trying to cover more ground rather than building everything up perfectly before moving on. But that is one thing I want to go back and actually get performance metrics on to know which one is faster because, for example, on some platforms, processes are expensive. So, maybe all those scannings are better even in incremental builds just to do it once. It also might change depending on how many sources are in your target and various other things. But again, it's not something we can know until we have performance metrics. And until we have that hammered down, I don't think we can expose what's in that cloud.
Right.
So,
Okay, thanks.
Misha. What's the biggest hurdle left to really making this usable for as many people as possible?
Well, just using modules in a wider situation, really. Modules have had a hard time getting off the ground because first the compilers didn't implement it, and then they did, and then you couldn't build them. Now you can. So the next step, I believe, especially once Basil gets it, is
Wait, are you saying that it's like suffering from a bad rap?
Lack of resources. So especially once I think the Basil folks get their hands on it and they start doing it as well, the next step is once we get using it, we can go file a bunch of bugs against the implementations to say this stuff doesn't work in a little bit more specific way. And then hopefully once that's there, more adoption comes, we get more implementation experience, we finally get the faster scanning and collation implemented, then we can start realizing the promises that modules have made for the past 5-6 years. So.
Hi. So you mentioned that we can't actually build this database until all of the source files are available. And so if your build builds a bunch of C++ code generators and then generates a bunch of files, you're going to have to build
At least
essentially all of your generated files before you can actually use the project in IDE. Is that correct?
So if you want the full one-stop shop build database.json, yes. You can access, there are other targets, CMake build database dash, I believe it's target name or something like that. You can, you can depend on, I know I'm working on this target, give me that target's build database. It'll give you only that target, it won't have like any of the dependency ones, but you can at least know like, oh, there's the name of it, I can go and figure out.
You can do that now in CMake? Ask for all the stuff for one particular target?
Yes, but it is just that target. There's no dependency information involved. Oh, yes. The question was, there's a way to ask for a build database for a single target. It is yes, but it is just that target. It will have references to any visible sets that aren't in that file. So you'll need to go and figure out which targets provide those sets.
Right. So if I was using an IDE that wants to consume this, then I would expect the IDE to just only depend on the giant build database, right?
Yeah, the simple implementation would be, but you can also work with the file API to be like, oh, it depends on these targets. And you can actually then go and be like, oh, I want those target databases too. And then it knows where they are. I can merge them in memory and then give you, you're working on this half of the project. You don't need to do the whole thing.
Okay.
But
it sounds related to your idea of generator support, because my project already has a target called all generated, so we can run static analysis on the generated files.
Mm-hmm.
And I'm going to need that in order to have the build database available.
There's a feature, I forget, is it already merged? Yeah. So there's now a feature in CMake called CodeGen, where you can do, there's a CodeGen target, which will build any custom command outputs for you, and just those. So yeah, look at that.
Oh, look at that.
So awesome. That you can probably delete a bunch of code. Yeah, I think it's 330 has it. If not, it'll be in 331. So.
Cool.
So how far away are we from that next step, that next boost?
Hopefully by next year we'll have incompatible flags within a project working, which means that if A is being consumed by B and C and they have different standards, A will compile BMIs for each. Currently we just use the BMIs that we compile here with A and then just hope that they're all compatible. But we'll eventually want to make synthetic targets for your target, for the project actual targets as well.
Has that been hard to do?
It's complicated because we're going to make BMIs during the compilation. So we already have one synthetic target that we're going to get modules from. So we need to basically, we also need to figure out what compatible means, which has been what I've been avoiding implementing. Because the list of flags that don't make things incompatible is woefully short. It's things like -v and please give me the perf of the compilation. Everything else seems to matter. So it's you end up looking at your build and you're like, oh, my five target project now has 1,000 things to do because everything has BMIs. But the nice thing is that we only build the BMIs that you actually use. So if you have 5 ways of using a target, you'll have BMI rules for all of them, but if you only import one from each, you'll only build those specific BMIs. So it's not all doom and gloom. All right. Thank you.